right, sound check and video check. Do I see my hand there? Looks like a yes. Okay, we are good to go then. Let's go ahead and mute that. Unplug this. Put headphones away. That's not how you put headphones away. Okay, that's better. This is even worse than last week. Last week I was 2 days late. This week I'm 3 days late. But hey, better late than never, I suppose. So, let's see. What are we doing today? I'm so discombobulated I don't even remember where we left off last time. We left with a problem, right? That's how we usually do it. Let me see what we have on this page. Ah, yes, this problem. Okay, I remember. So, a mechanic applies a force on a 2,500 kilogram car, causing it to move 25 meters. It initially is at rest. It reaches some final velocity of v and has a total work of 5,000 joules. So yeah, we can work that out pretty quickly. So that'll be the first item on our agenda. What else are we going to be doing today? We finished talking about work and kinetic energy and the work kinetic energy theorem last time, which tells us that total work equals the change in kinetic energy. Today we are going to introduce another type of energy, which is going to be potential energy, and also a third type that includes both kinetic and potential energy called mechanical energy. And we're going to go over something that a lot of teachers don't seem to go over, either because they don't understand it or because maybe I don't understand it. But we'll see who's right. We'll see if you find my arguments today convincing. And if you don't find my arguments convincing, then I can always win through the power of memes. I'm only half joking when I say that. You'll understand why later. Okay, do I have a backside to this? Yes, I do. So don't need a new sheet just yet. Let me think, is there anything else I need to talk about before we get started? Traditional office hours are definitely not happening this week either. At this rate, the traditional office hours might not be coming back fully until I'm done with this whole physics series. Which might be a good thing or a bad thing. Maybe I'd be better off just recording smaller videos for the kinds of problems that I want to explore in my traditional office hours. Maybe that would work better, just make videos dedicated to individual problems. But I don't know, I like the idea of office hours, just, having a stream available for people to come in and ask whatever questions they might have. I'll have to think about it. But anyway, let's get started. So, the problem we left off with. You have this force applied to a 2,500 kilogram car, causing it to move 25 meters horizontally. It starts at rest. It reaches some final velocity v after a total of 5,000 joules of work being done on the object. The questions were, what is the applied force and what is the final velocity? And you can actually answer these two questions in either order. It's not going to matter which one you answer first, because you don't need to know the applied force to get the final velocity, nor do you need to know the final velocity to get the applied force. They can both be calculated independently. So for the applied force, we can say if the applied force is the only force that's doing work, the other forces on this vehicle would be normal force upward and gravitational force downward. They cancel each other out, so that's one thing, even if they did do work. But the other thing is they are perpendicular to the direction of displacement. And if you remember the formula for work, it was the force times the displacement times the cosine of the angle between the direction of the force and the direction of the displacement. Cosine of 90 degrees is 0. So anytime the force is perpendicular to the motion, no work is being done by that force. So work due to normal force and work due to gravitational force are 0. The total work is just the work due to applied force. So work applied is 5,000. Work of the applied force equals 5,000 joules. That means force applied times the displacement of 25 meters times cosine of, let's see, the displacement is to the right and the force applied is also to the right. So the difference between right and right is 0 degrees, so that's times cosine of 0. And cosine of 0 is equal to 1, and that equals 5,000. Can I even squeeze it in there? Just barely. Okay, so we're left with 5,000 on the right, 25 force applied on the left. Divide by 25, easy peasy. Force applied would have to be, what, 200 newtons? If my quick math is right. 50 over 25 becomes a 2, and yeah, keep those 2 zeros. Yep, 200 newtons of force. So yeah, I guess one thing we can comment on here is it doesn't take a lot of force to move a car horizontally. 200 newtons is nothing compared to the actual weight of this car. If you took 2,500 times 9.8, that's almost 25,000 newtons of weight. But since we're not trying to lift it upwards, we don't need a lot of force. If you're just moving it horizontally, the only thing you'd be working against is friction, and it looks like in this case we treated the situation as being frictionless. So even an applied force of 1 Newton would have gotten this car to move in this sort of scenario. But there you go. That's finding the force applied. What about finding the final velocity? We can just use the work kinetic energy theorem and say that the total work is equal to the change in kinetic energy. Total work of 5,000 joules is equal to kinetic energy final minus initial, 1/2 mv final squared minus 1/2 mv initial squared. I'm going to factor out the 1/2 m. 1/2 2,500 factored out, and then multiply that by v final squared, which we just called v, minus v initial squared, which was 0. And there you go. We're pretty much done. To cancel the 1/2, multiply by 2 on both sides, so the 5,000 becomes 10,000, and then 10,000, or no, wait, not 10,000, 100,000 rather. 100,000 divided by, no, wait, 10,000, yeah. I'm miscounting my zeros. 10,000 equals 2,500 v squared. And then divide, well, we can divide by 100 and get rid of those 2 zeros, and now you've got 100 over 25, which is 4. 4 equals v squared, so v must be, I'm running out of space here. If 4 is equal to v squared, then v must be 2. We're just looking for the magnitude here, so only need to take the positive root. V equals 2 meters per second. And there you go. What some people will try to do here is they'll, like I warned last time, they will forget about the work kinetic energy theorem, and they will try to use this force to try and then calculate acceleration and do kinematics, which I suppose can work here since you also know the displacement, but you're going to run into situations where that's either not very doable, or just it takes too long to do it that way. So you are better off remembering that the work energy theorem is a thing that you can use. And that is it for the problem from last time. So today we want to talk about potential energy. Potential energy. Let's introduce the concept of potential energy. And along with it, we're going to be introducing a new type of work. So, what is potential energy and what is so potential about it? What does the word potential even mean? Well, think about how you use it in everyday life. Most people probably don't use the word potential in everyday life, but, you know, in common speech, we might say that, I don't know, we might say that, for example, a kid who's really enthusiastic about, let's say, science when they're still in elementary school, we might say that they are a potential doctor. It doesn't mean they are a doctor, they're just 5 years old or whatever, but they could be. So potential energy is energy that an object could have in the future. Energy that we can see the object having in the future due to where it is and what we know about the forces that will act on it if it moves from where it is. And that's not always going to be easily predictable for most forces. In fact, potential energy is only associated with, as far as I'm aware, 4 different forces. And those 4 forces are what I like to call the gems. The gems. 2 of which you will deal with in AP Physics 1 and Physics C Mechanics. We've got gravitational, or I'll just say gravity, electricity, magnetism, and springs. The gems. These are 4 sources of force that do have a potential energy associated with them, and there's a reason for it. We're gonna get to it. But yeah, just remember, if it's not the gems, there's no potential energy that can be calculated for it. So, friction, normal force, applied force, tension force, all of those other forces, no potential energy associated with them. It has to be one of these 4. It has to be one of those 4. And even for springs, there are some conditions. Oh, speaking of springs, I forgot to mention this, but I did edit the course plan to add some reading sections to the energy chapter for springs. I did not add any of the exercises and questions from that chapter because I didn't like them, and I think I have better ones from my from this book over here that I've mostly been using for our practice problems. So yeah, for practice problems, I'm gonna try and pick more of those spring problems to make up for the fact that I didn't like any of the spring problems that were in that section of the OpenStax book. Anyway, where was I? I got sidetracked. So, let's see. Let's start with gravity, I guess. So let's say I have an object sitting over here. Let's say it's a block of mass m. It doesn't really matter what the mass is. We don't have to assign a number to it. And let's say it starts at a height of h above the ground. Now, something that could happen in the future is that this box could find itself not having this cliff standing between it and the ground over here. So it could find itself in some future scenario where it's pushed out here, where gravity could act on it. The force of gravity is actually still acting on it even when it's up here, but force of gravity isn't doing any work here because, well, there is no displacement occurring. And then there's a normal force there. And yeah, if we remove this normal force, if we remove the surface that's underneath the object, then naturally the object will just go down. And when it does go down, how much work will the force of gravity do on it? How much kinetic energy does this object stand to gain due to the force of gravity? Well, let's see. Work due to gravity. I guess it's going to, if it does move in this scenario, it would move down like this. So it would have a displacement delta y equals, I guess, negative h. Right? It goes down by h meters. So it would be the force of gravity times the displacement. I guess I don't really need to put the negative sign in there, do I? Yeah, I can just use the magnitude of the displacement. Force of gravity times h times, and then cosine of the angle between their directions. Force of gravity is down, displacement is down, the angle between down and down is 0, and cosine of 0, as we know, is 1. So force of gravity will just be mg times that h over there, and there we go. The work done by gravity, the kinetic energy that this object would gain, this would be the total work, after all. This would be the total work. Since gravity is the only force acting on it, it's the only force doing work, so it's the only work we need. We don't have any other works to add to the total. So this would be equal to the change in kinetic energy of the object if it were to move from up here to down here. Okay, so it turns out that this is going to be the case no matter how the object gets from this height to this height. Turns out that'll be the case no matter how the object gets from here to here. If this object took a different path, if this object went down a slope, and let's say it's a smooth slope with no friction so that we don't have to do any calculations there. Let's say I'm going to draw a slope like this. Let's make sure it's at the same height. Yeah, that's about the same height. Let's say it's that same height h. And let's say it's a frictionless slope. And let's say our object just slides down this slope. Like so. I will call this L. Okay, what is the work done by gravity now? And is it still the total work? Well, it should be, because if we draw a diagram for the block as it's sliding down, so if I were to draw, here's the block at some point in time going down the slope, what are the forces acting on it? Well, we would have normal force this way. I think pink is too close to red. This was probably not the best choice. Force of gravity straight down. And that's it, because I said this was a frictionless surface. So yeah, there's nothing else. The normal force is perpendicular to the displacement. So work done by normal force is just normal force times L times cosine of 90. Cosine of 90 is 0, so no work done. So that leaves only the force of gravity doing work. So once again, total work is just the work due to gravity in this second scenario. So work total is equal to the work done by gravity is equal to the force of gravity times L times cosine of, well, let's see. Cosine of what? The force of gravity is straight down. L is in that direction, so I guess this angle over here, which is also this angle up here, that would be, we'll call it theta. Yeah, let's call it theta there. So times cosine of that theta. Well, what is L cosine theta? L is the hypotenuse of this right triangle. If you look at it, we've got a right triangle over here. L is the hypotenuse, and then the hypotenuse times the cosine is the adjacent to the angle. The side of the triangle that's adjacent to this angle would be this side right here. So L cosine theta is equal to H, which means this is just force of gravity times H, which means this is yet again total work equals your change in kinetic energy equals mgh again. As long as the path is smooth, I could have any path from this height to this height, and I would still have a change in kinetic energy due to gravity equal to mgh. So I could, let me draw a second copy of this scenario because it's kind of looking crowded over there. And let me actually switch colors. I could have an object starting over here at height h like this. And I could have it follow a path that looks like this, for example. I could just have it roller coaster slide its way down from here. Actually, it's not realistic for it to go above the height that it started from unless it was given some sort of initial kick. But, well, I never said that the initial velocity of this thing had to be 0. So for those who are worried about that technicality because you've read ahead, don't worry, it's still realistic if we assume that the box started with some velocity. The change in its kinetic energy doesn't require it to start at 0 after all. But yeah, if I take my box over here, give it an initial kick, and it slides around here, and let's say that this path, this track, is again frictionless. Actually, it doesn't even matter if there is friction here, as long as we're only focused on the work done by the force of gravity. We can calculate that alone. We don't have to set it equal to the total work necessarily. But let's just continue with the frictionless example for now. If we were to move on a path like this, well, now it gets a little bit more complicated because you have to chop up the motion into really, really small segments and calculate the work done along each segment. So, when the box is over here, you would have to calculate a tiny displacement that's in this sort of downward angled direction. There will be a normal force on it that's this way. Oh, would you look at that? The normal force is still perpendicular to, I guess we'll call this delta S at this point. So normal force isn't doing any work here. Okay, well, what about over here? Over here, the direction of its displacement would have to be this way, assuming that it's moving from left to right as I drew this curve. So I guess I'll call this delta S1 and I'll call this delta S2, and we'll call this normal force 2, and that's normal force 1. And no matter where you go, no matter which point you are at as you slowly track this thing's motion along this curved path, you notice that the normal force will always be perpendicular to the displacement at every single instant. So just like over here, normal force will do no work. Work done by normal force is still 0. Work done by normal force is still 0 over here. If you track it moment to moment, at every possible moment, no matter how the direction of the displacement changes, the direction of the normal force also changes, because the displacement is always parallel to this path, while the normal force is always perpendicular to it. So by necessity, they're always 90 degrees apart. So total work done by normal force is 0. We said the surface is frictionless, so that only leaves the force of gravity. And for the force of gravity, well, we already showed over here that the sideways parts of the motion don't do anything, right? This scenario over here, the second scenario we drew, shows that moving left or right doesn't matter. It's still going to be the same change in energy as if you moved straight down. So over here, we don't even have to do the horizontal part of this path. If we wanted to, we could chop this path up into little straight segments that look like this. And you can get as granular as you want with this. We could chop it up into straight segments like that. And for each of these straight segments, the ones that are at angles are just going to be treated like this. The horizontal part of it isn't going to do anything. The vertical part of it is going to give us work done by gravity due to, or proportional to whatever the change in height is for that segment. So for this segment over here, only this upward displacement would count. For this segment, there's no vertical displacement. For this segment, there's a downward displacement that would count. For this segment, we've got a downward, an upward, and so on and so forth. And of course, since the force of gravity is constant throughout all of this, I don't have to calculate the force of gravity at each spot and calculate and multiply it by the vertical displacement at each individual spot. Oops, that's supposed to be down, and that's down, and that's down. So I don't actually have to do it at every spot because it's the same force of gravity for each spot. So I could do force of gravity, if the gravity was changing, it would be force of gravity 1 times delta H, or I guess I would call it delta Y1, plus force of gravity 2 times delta Y2 for the second segment, plus force of gravity 3 times delta Y3, and so on, if I was doing it the hard way, segment by segment. But since force of gravity 1 and 2 and 3 and 4 are all the same thing, I can just factor it out. Since all of them are mg, I can just say that it's mg times delta y1 plus delta y2 plus delta y3, and so on. And what is the sum of a bunch of vertical displacements? It would just be the total vertical displacement between the start and end of the path, right? We did that way back in, what, our very first or maybe our second stream for this course. We discussed this idea that if you add a bunch of displacements sequentially from one starting point, step by step, to some final point, you get the same displacement that you would have gotten if you had simply calculated directly from the starting point to the ending point. So once I add up all these delta y's, what I end up with is this. I get delta y total being equal to negative h. So, yeah, I would still end up with mgh. I would still end up with mgh for the kinetic energy change due to gravity. So this is basically telling us that the work done by the force of gravity does not depend on the path chosen. All it depends on is the starting point and the ending point for the object as gravity acts on it. This tells us that work done by gravity, the official term, is independent of path. Work done by gravity is independent of path. This is a key point, and this is one of the reasons that gravity gets to be one of these forces that has a potential energy associated with it. In fact, all of these forces, we will find that the work done by them is independent of path if we were to sit down and analyze them, kind of like what we're doing over here. I'm not going to do that for the electrostatic force and the magnetic force because, well, those aren't really part of the course. And for the spring force, I don't know. I mean, with spring forces, there's only two directions to consider anyway, so I think that would be too trivial to work through, but I'll think about it as we approach talking about it. But yeah, this independence of path is an important feature for a force to have a potential energy associated with it. There's a second feature that these forces need to have, and that second feature is that the work done by them needs to be reversible. Work done by gravity can be exactly reversed, by reversing the path. This is something gravity can do that other forces, such as friction, cannot do. So let's see what I mean by this. So if I took this object over here and it went down by h meters to the ground, it will have gained mgh worth of kinetic energy. If I were to start with the object on the ground and have it rise h meters, the force of gravity acting on it is still down, but now the displacement is straight up. So what we would get is the change in its kinetic energy when rising, I'll call it delta Ke rise, is equal to the work done by gravity. Actually, I don't even need, hold on. I'll call it work gravity rise. Don't even need to refer to kinetic energy for this part, is equal to the force, which is mg, times the magnitude of the displacement is h, times the cosine of the angle between their directions. Now the displacement is up, but the force of gravity is still down. Up versus down, the angle between them is 180 degrees, and cosine of 180 is -1. This is going to be negative mgh, the exact opposite of the work done by gravity on the way down. So you gain mgh joules of energy if this object goes down by h meters, and you lose mgh worth of energy if the object moves up against gravity between those same two positions. You cannot do this with something like friction. What would happen with something like friction, or even normal force, or applied force, or tension force, or whatever? But I'll use friction since it's the classic example. If I have a block of mass m and I push it to the right x meters, if I push it by a distance of delta x, or a displacement of delta x rather, to the right, we know what the other forces on this are going to be. Let's use orange for this. We have normal force, which is perpendicular to the displacement and does no work. We have force of gravity, which is also perpendicular to the displacement in this case and does no work. And we will have a force of friction. I guess it would have to be kinetic friction here. And that will do work because it's not perpendicular to the displacement. We would say that the work done by friction in this scenario, work friction, I guess I'll call it right, is equal to the force of friction, whatever it is. I don't particularly care about, writing it out in terms of the mass and the friction coefficient here. We would say this times the displacement, so times delta x, or at least the magnitude of delta x, times cosine of, well, that would be cosine of 180 degrees, which is going to be a negative, so whatever this force of friction is, some constant that can be figured out once you have the necessary information, you're going to get some sort of negative work done. The object is going to lose energy to friction. That is very believable. Things tend to slow down, lose kinetic energy due to friction. So that's not surprising. Okay, what happens if after it's been pushed over here, so let me extend this, what happens if after I push the box over here, what happens if now I push it back? Let me do another color for this. What happens if I push it back like this? Do I get positive force of friction delta x? Well, no, because if you change the direction, the friction force also changes its direction. The direction of the friction force also has to change in order for this to even be possible in the first place. In this case, the force of friction is going to be to the right. So once again, you have a scenario where the friction force and the displacement are going to be opposite of each other. So you're still going to get same magnitude friction, same magnitude displacement, and same cosine 180. So you lose energy either way. Reversing directions, reversing the displacement of the object doesn't reverse the work done by friction. Work friction left, work friction as you go to the left is also the same magnitude friction, whatever it was before, it'll be the same amount after, same magnitude of displacement, and the angle between the two new directions is still 180 because they both flipped. So yeah, this is not the negative of this. If I add these together, the total is not zero. So the work done by the force of friction is not reversible. You can think about what happens with other forces too, like I guess normal force. If you drew a box, say, being lifted up by normal force or tension force, using an elevator in the case of normal force, or just a rope pulling it up in the case of tension force, if you wanted to reverse the direction, you would have to introduce another force. You would have to introduce another force in order to reverse the direction in the first place. And that force wasn't there on the way up, so now you haven't perfectly reversed the work that you did on the way up if you're trying to move the block back down. So unless you have these two properties, but also the other thing is the work done by forces like normal force and tension force, and friction force for that matter, depend on the path. So that alone is a disqualifier. So yeah, tension, friction, normal force, most forces that we deal with don't have these two special properties that a force like gravity has. Any force that does have these special properties is called a conservative force. Any force that has these special properties is called a conservative force. What makes a force conservative? These two things. No, it has nothing to do with how they voted in the last election. Conservative forces are conservative because of these two traits. If they have these two traits, then they are conservative forces. So yeah, your conservative forces are just the gems, as I stated earlier. And in the case of springs, it's specifically for springs that obey Hooke's law, because there are some non-ideal springs. So this is only true for ideal or Hookean springs. Real springs, however, tend to have some friction, and also their mass tends to mess with things a little bit. So in an ideal world, that's what we assume when we are working with the spring force. If we don't assume that, then the conservative properties of the spring force disappear. So now that we know a little bit more about what makes a force conservative, let's talk about another concept that is useful to us. So we've talked about the total work, which is just calculating the work done by each and every force and adding them up, or calculating the net force and then getting the work due to that. We showed both methods last time. So we've talked about total work, which is equal to the change in the object's kinetic energy. Now I want to introduce the concept of conservative and non-conservative work. Now I want to talk about the idea of conservative and non-conservative work. So we can say work conservative, I guess we'll just call it WC, is just the part of the total work done by conservative forces. And this conservative work is the reversible work. It's the work that can be reversed by simply reversing the path of the object. Versus the more interesting concept probably is the non-conservative work, whatever is left. If you were to relate this to total work, so work non-conservative would be total work done by non-conservative forces. Total work done by non-conservative forces. I probably should have changed colors here. By non-conservative forces, and that's probably too small for most of you to read anyway, but thankfully I say what I write out loud. Okay, so conservative work, total work done by conservative forces. Non-conservative work, total work done by non-conservative forces. Makes sense. And then of course we can say that the total work is just the sum of these two, right? Because a force is either conservative or non-conservative. So the total work is just going to be the sum of the work conservative plus the work non-conservative. Okay, but the total work is equal to the change in kinetic energy. as we know from the work energy theorem from last time. The work done by conservative forces, we associate this with potential energy. So potential energy is the energy that an object, quote unquote, has because of what it could gain in the future. So we don't want to actually use the conservative work as is over here. The conservative work is that potential energy already being converted into kinetic energy. The conservative work is us already calculating what could happen in the hypothetical future where, in the case of our box example up here, where it already traveled down by h meters. So that's not what we want. The conservative work is not the potential energy. Rather, it is the reverse of the potential energy. Hold on. This isn't the best way to explain this. Let me think about this. I mean, I know what this is supposed to be. This is supposed to be the negative change in potential energy. But trying to justify it in an intuitive way, I think I approached this the wrong way. Let me take a step back and think about this. I guess I never really defined potential energy in the first place. So potential energy that an object could have, we discussed that. Energy that an object could have in the future if it moves from one position to another. So when the object is up here, it could gain mgh worth of energy if it manages to move down here. So we would say when it's up here, its potential energy is mgh. When it's down here, well, it already gained all that energy, so there's no more potential energy left unless you dig a hole underneath it, allowing it to fall even further and gain more energy, but we'll worry about those kinds of scenarios later. So yeah, potential energy is mgh when you're up here. When you go down here, when the conservative forces do their work, you lose that potential energy, and in its place you gain the actual kinetic energy that you predicted you would gain. So yeah, work done by conservative forces therefore is equal to the negative change in potential energy. Oh, and by the way, the symbols I use. So last time I commented, I would hope I remembered to comment on how I use KE for kinetic energy. Some books and some teachers like to just use K. And for potential energy, I like to use PE, but I know the AP exam, for example, uses a capital U to represent potential energy, which I think is not very intuitive. So I would, at the very least, when you're first learning this, I would rather use PE because, the PE tells you right away what it is, and once you get used to it later in the course, maybe switch to using this U just to prepare for the AP exam. So that's just my little side comment for that. And I'm going to leave a space here for one more type of energy. Where was I before I went over here? Right, so we just said the work done by the conservative forces, once they actually do the work that we pre-calculated, the object loses that amount of it loses that potential energy and gains it as kinetic energy. And then the non-conservative work is interesting. So non-conservative work, we define it. I want to try and get this all on one page, so I guess I'll do it over here. Work non-conservative, we define this as the change in an object's mechanical energy. We define this as the change in an object's mechanical energy. So that's delta ME. Of course, the alternative symbol, usually they will just refer to it as E. But I will use ME for now, since this is new to most, if not all of you. Okay, if I rearrange this by adding delta PE to both sides, then what do I get? I'll write it down here in the corner, and this will be the last thing for this page before I grab a fresh one. I will get change in kinetic energy plus change in potential energy equals change in mechanical energy. In other words, mechanical energy is simply the total kinetic and potential energy that an object has. Mechanical energy final minus mechanical energy initial equals kinetic final minus kinetic initial plus potential final minus potential initial. Or if you don't have an initial and a final point, if you're just talking about an object at one specific point, then mechanical energy at that point equals the object's kinetic energy at that point plus its potential energy at that point. So that's the difference between the version with the deltas versus without. So there's mechanical energy defined mathematically, and same deal for potential energy. We're not really going to bother much with calculating the conservative work. So remembering that conservative work is equal to negative change in potential energy, not the most important thing. I guess we might use it a couple times here and there to prove a few things, but for most problems that we'll be solving, that would be like the lowest priority to remember. So I would recommend focusing much more on this relationship over here. Non-conservative work is equal to change in mechanical energy, and the work energy theorem, total work is equal to change in kinetic energy. If you remember those two, then you should be good to go. And of course, this as well, that mechanical energy is the sum of kinetic and potential. If you put all those together, that should make up for you ignoring this last one. You can afford to ignore that work done by conservative forces is negative change in potential energy. You can afford to ignore. Can afford to ignore as long as you have all the other pieces of the puzzle to put together. Can afford to ignore. Where to move to from here? I guess we could do a problem, or we could talk about conservation of energy. Let me think. I think we should talk about conservation of energy first. But before that, so to recap, potential energy. A lot of students are taught that potential energy is stored energy, and that's not really the case. I guess let's again do this illustration. Oh, and I need to talk about the fact that potential energy is relative as well, so that's another thing that I need to do. Okay, so again, we've got a block over here at some height h. Actually, I'm going to call this h1. And we would say that its gravitational potential energy, we saw consistently that it's just going to be the mass times the acceleration due to gravity times h. That's the formula we typically use, where h is typically set to 0 at the lowest point. In fact, what I should say is change in potential energy gravitational. This is the more correct definition, is equal to mg times delta h. That's what I should be saying. This is the more accurate definition, more accurate of gravitational potential energy. So a lot of people will say that potential energy is like this stored energy, but that's not really true if you think about it, because suppose you have this object over here and it's at some height h1, and we would say then while it's up here it has mgh1 worth of potential energy. Well, is that really the case? And where is that energy stored if it actually has it? In what way does this object have mgh1 worth of energy? And if I were to dig a hole over here to a depth of h2, if I were to dig a hole underneath this object to a depth of h2, well, does it now gain more energy in its storage somehow? How does digging a hole over here, not interacting with this object, change its potential energy from mgh1 to mgh1 plus h2? How does digging a hole down here somehow beam energy up to it? That doesn't make any sense, right? So it's not really stored energy. Like I said in the beginning, it's called potential energy because it's energy that an object doesn't have necessarily, but could have in a hypothetical future if it follows a certain path. If this object were to move from here to here, it will get mgh1 worth of kinetic energy. And if it were to move from here all the way to the bottom of this hole that I dug down here, then it will gain mg, and then the sum of h1 and h2 worth of kinetic energy. So really the only energy here is kinetic energy. It's just a difference between current kinetic energy and future kinetic energy. In fact, this is even true for other types of energy. This is true for electricity, because if you think about it, electricity is really just the motion, the kinetic energy, in other words, the motion energy of electrons moving through a circuit. What about heat and thermal energy? Well, that's associated with the vibrations of atoms, how quickly they're vibrating and colliding with each other. That's movement energy, that's kinetic energy. So in order to make sure that you don't forget this, I have put together a little photo that I think some of you will enjoy. The rest of you will probably cringe at it, but that cringiness is probably what will make it memorable. Here you go. Wait, it's all kinetic energy? Yes, it always has been. You're welcome. Potential energy is not actually stored energy. And I guess I forgot to comment on, the image reminded me, chemical energy. What's chemical energy really? All energy in chemistry is really just electric energy. It's all just electrostatic forces, protons and electrons pushing and pulling at each other. And we already said that electric energy is really still just kinetic energy, either present or future. So, yeah, it's all kinetic energy. I don't know what to tell you. Now, what else do I need to talk about? Oh, right, the relative nature of potential energy, whether it's gravitational or electric or magnetic or spring potential energy, which I like to call it spring potential energy anyway, but textbooks will officially call it elastic potential energy because you could get that energy from, say, a rubber band, for example. It doesn't necessarily have to be an actual spring. As long as the material pulls back when you pull on it and pushes back if you push on it, and the amount of pullback or pushback is proportional to the length to which you stretch or compress it, then it can work. And of course, some objects like rubber bands can only be stretched and not compressed, so there's that little caveat. But anyway, all potential energy is relative. There is no absolute potential energy. And what does that mean? What that means is I can't actually say that this object has mgh1 of potential energy when it sits here unless I can say beyond a shadow of a doubt that at this line over here, at this height, potential energy is equal to 0. It's convenient to set it equal to 0 at a point like this, or even over here. Typically, the lowest point is the best point to use for gravitational potential energy because it eliminates situations where you have to deal with negatives and just makes the math a little bit easier to deal with. So it's a clever choice, but there's no actual physical reason why the ground level has to be 0 in terms of potential energy. You can set your 0 to wherever you want. All that matters is changes in potential energy. This object might have a potential energy of mgh1 relative to the ground, but it has a potential energy of mgh1 plus h2 relative to the bottom of this hole. So, yeah, pick a point that you want to use as your 0 reference line, as we like to call it, or just 0 line, as some people call it, and determine your potential energy relative to that. But just remember, there is no absolute potential energy. It's all relative. And later on, in a future chapter, we will take another look at gravitational potential energy using a different formula for gravity, where actually the ground will be the worst place, or one of the worst places, to set your potential energy to 0. We'll talk about that when we get to it. Usually where you set your 0 of potential energy, usually the position where you set your potential energy to be 0 is going to be decided based on just mathematical convenience more than anything else. So that's my mini lecture on potential energy being relative. Now then, where do we need to go next? Next is conservation of energy. conservation of mechanical energy, to be more specific. Conservation of mechanical energy. You've probably heard of the law of conservation of energy before. Specifically, you may have heard of the first law of thermodynamics. That's not what we're doing here, but let's talk about the first law of thermodynamics for a minute. So, first law of thermodynamics says what? It says energy cannot be created or destroyed, but can be changed from one form to another. All the forms are kinetic energy anyway. But I digress. First law of thermodynamics. Energy cannot be created or destroyed. And yes, Einstein throws a wrench in that. I know some of you are far ahead of this course, but let's stick to classical mechanics for now. Let's stick to classical physics. Energy cannot be created or destroyed. If energy is lost in some place, an equal amount needs to be gained somewhere else. This applies to all forms of energy. This is for all forms of energy. This is for all forms of energy. Including mechanical energy, thermal energy, chemical energy. What am I missing? I guess those will have to do for now, because my brain's kind of fried. It's been a busy week. I probably should have postponed today's stream as well, but I've postponed this stream by 3 days already, so I figured the show must go on, and here I am, so you're stuck with my partly dysfunctional brain today. I imagine I might catch some mistakes while reviewing this and time-stamping it later on, and if I do catch any mistakes or things that need to be corrected, I'll post a pinned comment or something. Anyway, so first law of thermodynamics applies to all forms of energy, but mechanical energy is only one of those forms, so mechanical energy is not always conserved. When mechanical energy is not conserved, we are not violating the first law of thermodynamics, because usually any mechanical energy that's not conserved gets lost in the form of typically heat. For example, if you're dealing with a situation where there's friction, well, I mean, you can feel it if you rub your hands together, right? That's how you warm up in the winter. You're converting some of your mechanical energy into thermal energy. So, first law of thermodynamics holds, whatever mechanical energy you lose when rubbing your hands, an equal amount of thermal energy is generated. So we're not violating the first law of thermodynamics if mechanical energy is not conserved. Mechanical energy conservation is not a given. There is a condition for mechanical energy to be conserved. For mechanical energy to be conserved, the only work that can be done on an object must be, can you guess from the name? Conservative work. For mechanical energy to be conserved, all work... Well, actually, no, wait, no, that's the wrong statement. the total non-conservative work, must be 0. The phrasing here is really important. I almost phrased it incorrectly there. You'll see why in a minute. You'll see why what I was about to say earlier was wrong. The total non-conservative work must be 0. That is to say, work non-conservative must be equal to 0. And we can see this mathematically because earlier we said, what is the non-conservative work equal to? Well, we said it was equal to the change in mechanical energy. For mechanical energy to be conserved, it must not change. It must not increase or decrease. So delta mechanical energy has to be 0. ME is conserved if that mathematical statement over there is true. Now, what I was about to mistakenly say is that all work done must be conservative. That's not true. You can have non-conservative forces doing work on an object, and as long as those non-conservative forces and the work they do, as long as that work cancels out, you're fine. Your mechanical energy can still be conserved, which is why you can still have conservation of energy in scenarios where tension, normal force, well, maybe not friction, but tension and normal force and applied forces and most other forces except maybe air resistance and friction. You can have those forces be present but still have a total non-conservative work of 0 despite their presence. And we will see examples of that. In fact, we're probably ready to look at examples right now. Let me think. Are there any other details I need to go over? Actually, yes, one more thing. Let's expand this equation a little bit. I think the more important takeaway here is it doesn't matter whether mechanical energy is conserved or not. Whatever the non-conservative work is, if mechanical energy is not conserved, then you will usually have the means to calculate this, so you'll still be using this equation anyway, regardless of whether there's an equals 0 here or not. So let me switch colors because it's been a bit. So if I take my work non-conservative and set it equal to delta ME, I'm going to rewrite my delta mechanical energy as mechanical energy final minus mechanical energy initial. Whoops, mechanical energy initial. And I'm going to add mechanical energy initial over to the left. So mechanical energy initial plus work non-conservative is equal to mechanical energy final. And then mechanical energy initial is just going to be potential energy initial plus kinetic energy initial. Usually I write it the other way around with kinetic energy first, but it doesn't matter. Addition works both ways. And then mechanical energy final would be potential energy final plus kinetic energy final. Now, potential energy here includes all types of potential energy that could be present in the problem. So if gravity is involved, it includes gravitational potential energy. If springs are involved, it includes the spring or elastic potential energy, as textbooks like to call it. The same thing with kinetic energy. There's actually going to be a second type of kinetic energy we will learn about later on. But for now, the only kinetic energy we know is the 1/2 mv squared type. But later on, this may include two terms for both initial and final, of course. And of course, when the mechanical energy is conserved, you just substitute this with a 0 and you're good to go. I would rather just remember it this way, so that if this term is a 0, you can just strike it out and keep going, and if it's not 0, then you're not sitting there twiddling your thumbs trying to figure out what to do. I think the reason that a lot of students get stuck when they face a situation where mechanical energy is not conserved is because they don't realize that as long as you calculate what this total non-conservative work is, you can still continue the problem. It's really just changing one term in your mechanical energy equation, adding or subtracting it. But yeah, a lot of students get taught this formula without the work non-conservative part being written in it. Usually, like, their teachers will give them this, but then they just kind of mentally brush it aside, both the teachers and the students, and I don't know. I like to emphasize this. In fact, another thing I like to do is I don't like the habit of just declaring that energy is conserved when you begin a mechanical energy problem, because a lot of students will just kind of declare it without really remembering the condition for it. The condition is that the non-conservative work needs to be 0. Did you actually stop to determine that this was the case? A lot of times I see students just assume that's the case, and that's not a healthy habit to have. That will run you into problems whenever it's not the case. Okay, so that's my mini rant/lecture on conservation of mechanical energy aside. Let's do some problems. I'm sure that's the moment that a lot of you have all been waiting for, so let's see what kinds of problems we can find. And I guess I will have to, at some point, stop to talk about elastic potential energy as well, and talk about its formula. We'll get there. Let's do a problem or two and then introduce that, probably through a problem. Let's see. We have a Daredevil on a motorcycle. Oh boy, this is going to be fun. A Daredevil on a motorcycle leaves the end of a ramp with a speed of 35 meters per second, as in the figure, which I will draw for you. If his speed is 33 meters per second when he reaches the peak of the path, what is the maximum height that he reaches? Ignore friction and air resistance. Okay, so this person is riding up some sort of bike ramp, and they take off at 35 meters per second. I guess the way they've illustrated it, they meant for him to be at 35 meters per second there. So V initial equals 35 meters per second at whatever angle. They don't actually tell us the angle. And they leap into the air on their motorbike. To some currently unknown height. And up here, their velocity is 33 meters per second. So it says, what is the maximum height that he reaches? Ignore friction and air resistance. Okay, what are the forces acting on this person when he moves from here to here? So what I like to do to organize these problems is I like to pretend I'm a movie director and separate everything into a bunch of scenes. I like to separate things into a bunch of scenes. In this case, I guess you don't really need that because there's only two scenes, the beginning and the end over here. But we will see problems where you have multiple points in time that you need to consider, and for those I really like separating them into scene 1, scene 2, scene 3, and so on. I feel like that just helps students mentally organize things a little bit better. Okay, so over here, what forces are acting on this person? There's the force of gravity acting on them, which is conservative. There's the normal force acting on them, which is not conservative, but that's okay because the normal force is going to be perpendicular to this person's motion. This person is moving parallel to the ramp at all points here, and the normal force is perpendicular to the ramp at all points. When the force is perpendicular to the displacement, we've said this how many times today? It's cosine of 90 degrees when calculating the work. Normal force is normal force times whatever the displacement is times cosine of 90. Cosine of 90 degrees is 0. So it's okay that a non-conservative force is present here because the work done by it is 0, and even if it was not 0, we would just calculate whatever it is if we could and plug it into our mechanical energy formula and still get a result. So, like I said earlier, does not matter whether the mechanical energy is conserved or not, as long as you can determine what the non-conservative work is one way or another, whether it's 0 or some other quantity. So, other than normal force and gravitational force, is there anything else? They said ignore friction and ignore air resistance. I see no ropes, so no tension, and I see no springs, so yeah, I think we're done. And then up here, the only force acting on them, of course, would just be the force of gravity. I don't need to worry about the force of gravity since it's conservative. That will be accounted for when we calculate the potential energy changes. So work non-conservative plus kinetic energy plus potential energy initial equals potential energy final plus kinetic energy final. So non-conservative work plus kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. The non-conservative work we already determined is 0. Kinetic energy initial is 1/2 m times v initial squared, plus potential energy initial is mg times h initial, whatever that may be. Kinetic energy final is 1/2 m times v final squared. And then potential energy final would be mg h final. Gravitational potential energy is the only type that we need to consider for this problem, so yeah, we are done. They never told us the mass of this guy, and it turns out it doesn't matter, because if I just divide by m throughout in this equation, it just cancels out everywhere. That could have been a problem. If our non-conservative work was not 0, we wouldn't have been able to get away with that. But since it is 0, we can divide 0 by m and still have a 0, and yeah, that eliminates the need to know the value of m. And since we don't really enjoy dealing with fractions that much, let's multiply everything by 2 to get rid of those 1/2. So that gives me v initial squared plus 2g h initial equals v final squared plus 2g h final. Some of you might see something familiar in this. You might be seeing a kinematics equation in there. Your eyes do not deceive you. That is kinematics. So h initial would be the height over here. Let's set it to 0. Let's say that h initial over here is equal to 0, while h final up there is equal to what they just called h. Okay, so that means this is now 0. And I can do... I'll subtract v final squared on both sides, so v initial squared minus v final squared equals 2g h final divided by 2g. We get 35 squared minus 33 squared over 2 times 9.8 equals, h final was just the h that they wanted us to find, and yeah, plug in the numbers. The units are correct, right? Yeah, 35 and 33 are in meters per second, and 9.8 of course is in standard units, and the 2 is just a constant that has no units to it. So yeah, we are good in terms of units. We should be getting height in meters if we do this. 35 squared minus 33 squared is 136, and then divide that by 19.6, and I'm getting 6.9387. I'll round that to 6.94. So I'm getting h is equal to about 6.94 meters. Sounds pretty realistic if you ask me. Notice, by the way, with this problem, that we did not need to know the direction of the initial or final velocity, right? Kinetic energy only depends on the square of the magnitude of the velocity. Direction isn't really going to matter. Although, if I were to ask you the follow-up question now, what is the angle of projection? At what angle did this motorbiker launch off of the ramp? You could do that. In fact, you could have done that before we did any of this math, if you remember stuff from our projectile motion chapter. You might remember that if gravity is the only force acting on the biker when they're in the air, then only the vertical part of their initial velocity changes, their horizontal part stays the same. So you would conclude that the horizontal component of the 35 meters per second they had over here must have been 33, and from there 33 over 35 must have been equal to cosine of theta. Take your inverse cosine, and there you go. That's a mini review of projectile motion. Oh, here's another one that throws a bit of a wrench in your preconceived notions. Get ready for this one. So it says a softball pitcher rotates a 0.25 kilogram ball around a vertical circular path of radius 0.6 meters before releasing it. So they have, you know how baseball pitchers kind of just swirl their hands. They just, I can't fit my hand, my whole entire arm here in front of the camera to show you, but you know the move where they just kind of roll their entire arm around in a circle before they throw. Something like this. So yeah, they roll their hand and then they throw the ball out. So it says a 0.25 kilogram ball around a vertical circular path of radius 0.6, or no, a softball pitcher rotates a 0.25 kilogram ball around a vertical circular path of radius 0.6 meters. So radius is 0.6 meters. It's good that they had it in meters for us before releasing it. The pitcher exerts a 30 Newton force directed parallel to the motion of the ball around the complete circular path. So force is 30 newtons. Force applied is a constant 30 newtons parallel to the path. This is important. Parallel to the path. We'll pick this apart in a minute. The speed of the ball at the top of the circle is 15 meters per second. If the ball is released at the bottom of the circle, what is its speed upon release? So I guess it was moving at v top equals 15 meters per second. And then they probably rotate their arm 2 or 3 times, and then I guess they did an underhand throw. I should be moving my hand this way. They do an underhand throw, and they eventually throw it out like that at what is V bottom? That is their question. Okay, so here it's very easy to make the following mistake. It's very easy to go, well, if the force applied is parallel to the ball, so let's see, at the top its velocity would have been this way, to the left, then some people might say, well, the force applied is to the left, and then the displacement from here to here is straight down, so the total work is 0, right? Wrong. Because here, the force applied is not constantly to the left. Here, the direction of the applied force is changing with the direction of the ball's motion. So if I were to chop up, I guess we'll assume that they just did it in a half circle to make things easier for ourselves. We'll say that this was the path taken. So if we were to chop this up into small segments of motion, kind of like what we did earlier with this curved path, we kind of said, you can chop it up into little straight segments. If we were to chop this up into a bunch of straight segments, then they would look something like this. I didn't draw it very well. It kind of looks like half of an oval rather than a circle, but you get what I'm trying to convey here. If we were to divide it into a bunch of straight segments like this, then what it's actually saying is that for each segment, the displacement is going to be, for that really, really small section, there's going to be a tiny amount of displacement. I'll call it delta S. And the force applied is also going to be in that same direction. And as the ball moves, the person is also turning their hand around and therefore turning the direction in which they apply that force. So when the ball is over here, for example, their force applied is now this way. And the displacement is also in that direction. And so on and so forth. So really, this is essentially the same as if you took all these segments and just kind of unstretched this. Let me see if I have something string-like to illustrate the idea. I guess we'll use this thing, this charger cable. So essentially, what we're doing here is if you just took all these little segments and straightened them out like this, you end up with a scenario that is basically all the segments laid out straight like this, and the force applied for each segment is going to be in the same direction. So that's the direction of the force. And then the displacement for each of those segments is also in that same direction. So those are your little delta S's. And if you add all that up, then essentially what you have is just a force being constantly applied in one direction, and your total displacement being in that same direction. So this I would call delta S total, the sum of all of those little delta S's, which isn't really a displacement anymore. Rather, it's a distance. So in this instance, what we actually want to do to calculate the total work done by the force applied is take that force applied, work done by the applied force, take that force applied, 30 newtons, and multiply it by the total distance around this semicircle. And that distance is going to be half of the circumference, so 1/2 of 2 pi r. 2 pi r with r being 0.6. Okay, so 30 times 1/2 times 2 pi r times cosine of, well, 0 degrees, because at every instance the direction of the applied force is the same as the direction of the displacement. Did I break any rules here now that I'm using distance instead of displacement? No, I just, instead of doing the tedious process of adding up a bunch of little displacements that are going to be multiplied by the same force applied, I did basically the same thing that I did over here earlier, where because the force was the same for each of these little displacements, I factored out the force. I factored out that force applied, and I added the magnitudes of all of those little displacements. If you're adding the magnitudes of the displacements, the magnitudes are scalars. So they just add like scalars. They don't add like vectors. So that's why all these little displacements are adding up to a distance, and they're not adding up to this, what would we call it? 2 times 0.6. They're not adding up to this downward displacement of 1.2 meters. They would add up to 1.2 meters if I was adding them as vectors, but I'm not adding the displacements themselves, I'm adding their magnitudes. So really it's just a consequence of the math. Sometimes you will have to do that in Physics 1. You will have to realize that even though the path is, twisting and curving like this, the force is also moving in such a way that it has the same angle with the path that it did at the beginning. And in those cases, essentially, your work formula just becomes force times total distance times cosine of whatever the angle was at the start. That angle presumably would be kept throughout the entire motion. If anything rotates, if the direction of the displacement rotates, the direction of the force rotates by the same amount of degrees with it, in that case, then yeah, your cosine theta would also be something that, like the force over here, gets factored out. Come to think of it, I should have put that in here. Yeah, there should have been a cosine 0 over here that also gets factored out. But it being cosine 0, I think, tells you why I didn't bother writing it back there. It's just equal to 1. So it's not really doing anything. Multiplying by 1 doesn't change things. But in case of a situation where it does matter, I would make sure that I stay in the mental habit of remembering that cosine part of my work formula. Anyway, if we go ahead and plug in our numbers, we get half of 2 pi is just 1 pi, and then 0.6 times 30, what's 0.6 times 30? That's the same as 6 times 3 is 18, so it looks like I am left with 18 pi. Work due to the applied force is equal to 18 pi joules. And that's non-conservative work. That is non-conservative work. The applied force is not a conservative force. The only other force acting on this ball is gravity, and that's a conservative force, so we will account for it through potential energy in our mechanical energy formula. So let's go ahead and write that. Kinetic energy initial plus potential energy initial plus work non-conservative equals kinetic energy final plus potential energy final. Kinetic energy initial is 1/2 of the mass. In this case, the mass does matter because our non-conservative work is not 0. What was the mass again? It was 0.25. I forgot to list it. The mass of the ball is 0.25 kilograms. Pretty reasonable for a baseball. So 1/2, I'll just write it as m here. V initial squared plus mgh initial plus the non-conservative work is 18 pi. Positive, which means it's actually going to have more energy at the end than it did in the beginning, which makes sense because the baseball player, by applying a force to the ball, is adding energy to it. That makes sense to me. If there was friction and air resistance to take into account, I would expect my non-conservative work to be negative. That's another mistaken assumption, by the way, that some students will make. They will assume if energy is not conserved, that the final energy is always less than the initial, which is not true. Sometimes it's less, sometimes it's more. It depends on what the non-conservative work is doing. What are the non-conservative forces doing? Are they adding energy or taking away? Or some combination of both, in which case you have to determine whether there's more being added or more being taken away. But I digress. 1/2 mv final squared for this side and mgh final. I know it can be a hassle to write this out every single time, but I am going to do it for a while because it matters. Actually, I'm probably going to do it for the whole course. Who am I kidding? It matters. It's good practice, even if you already know that some of these are zeros that you can strike out. It's good to, when you're first learning this, write out all the terms, because it helps you just memorize the formula better as well. I know you get a formula sheet, but we've talked about this many times before. I do not care that you get a formula sheet. Having the formulas in your head is faster than flipping back and forth between your formula sheet and your test booklet. Or I guess you guys are doing parts of the test on a computer this year. But still, flipping back and forth between a formula sheet and the problem you're working on, it does things to your brain. In addition to wasting precious seconds that slowly but surely add up, it also just does something to your brain when you're constantly redirecting your attention from one thing to another. It's not good. At least I don't think so. Mini rant aside though, let's go ahead and substitute some values here. 1/2 of 0.25 times V initial squared. I guess in this case I called it V top, so don't take initial and final literally. Think of these as V in position 1 and H of position 1 and V of position 2 and H of position 2. And of course there could be a position 3 and a position 4 and so on. Like I said earlier, you might have more than 2 scenes. We'll see problems like that soon enough. But anyway, 1/2 0.25 times V top squared, so that's 15 squared, plus mgh initial. How am I going to define h? I'm going to say that h equals 0 down here at the bottom. Pretty reasonable assumption. H bottom, I'm going to set that to 0, which means h top is 1.2 meters, right? 2 times the radius from the bottom to the center, and then from the center to the top. 0.6 plus 0.6. So h initial then would be h top, which is, 1.2. So 0.25 times 9.8 times 1.2 plus 18 pi. So that's one side of the equal sign. Equals 1/2 mv bottom squared, so 1/2 0.25 times, well, we don't know v bottom yet. That's what we're trying to solve for. Plus 0.25 times 9.8 times h final, which is h bottom. We've already set that to 0, so luckily we can just eliminate that term. All we have to do now is, let's see, 1/2 times 0.25 is 0.125, and then divide 0.125 over to the other side of the equation, and we're good to go. So let's go ahead and put all of that into our calculator. 0.5 times 0.25 times 15 squared for our first term, plus 0.25 times 9.8 times 1.2 for our second term, plus 18 pi. Here's where we're going to get the ugly numbers. I'm getting 87.613667776, and then that divided by 0.125 gives me 700.909. So 700.9093421 is equal to v bottom squared. And if I take the square root on both sides, I only need the magnitude, so we'll take the positive root only. We don't need the negative root. And we get v bottom equals about, I'm going to round it to 2 decimal places, I'm getting 26.47. 26.47 meters per second. Does my result make sense? Well, it is faster than 15, which makes sense for 2 reasons. It dropped in height, so gravity did positive work on it, so that should have added to its kinetic energy, so it would have sped up just due to that alone. But on top of that, there was an applied force that was in the direction of its motion at all points through this arc, and that should have also added to its kinetic energy. So yes, it does meet my expectations. It is faster than it was at the top, and not unreasonably so. I don't know what the world record is for fastest baseball throw off the top of my head, but I would assume 26.47 meters per second is reasonable and somewhere at or below that. All right. Now let's look at I think now it's time to talk about springs and elastic potential energy before we dig into some more problems. And we're still going to have over an hour left, it looks like, for problems, so that'll be good. I mean, I know I said last time that we would probably be done with energy in just 3 episodes, but I was kind of expecting my estimates to be off by a bit. Okay, so springs, elastic potential energy. Let's see how this works. So I'm going to draw a graph here for spring force versus, I guess I'll call it X. And over here I'm going to draw a diagram of a spring that is originally at this length but then I'll draw it again, but then it gets stretched out. To, let's say, this length. Whoops, I wanted that to look, yeah, something more like that. There we go. And then I guess over here I'll draw the table underneath as well. Have that. And I guess I will have, what do I even want to put here? I guess I should put something like a block. Actually, let's reverse the situation. Let's say this is the original length. And there's a block here of mass m. And let's say that this surface is frictionless. So frictionless surface. Frictionless surface. And let's say that from here I compress it by some amount. Over here I compress. And I'm about to let it go. If I let it go, how much kinetic energy will this thing gain? What is my possible future kinetic energy? Not guaranteed, but possible future kinetic energy if I were to let this block go from this position where the spring is compressed. So here, spring is at rest. Here, spring is compressed. Just to make that extra clear. Probably should have thought ahead and drawn this one below this one, but what can you do? That's one of the downsides of using pen. I can't just erase and start over, and I don't want to use up more paper than I have to. So in this case, the spring is going to decompress all the way up until it reaches this point. All the way up until it reaches this point. So the total displacement is going to be by this much. That's going to be delta x. I'm going to call it dc for decompression. That's going to be the decompression displacement. But you can't just calculate whatever the spring force is at this moment and multiply that by this delta x, because the spring force here is not constant. The work formula that we've been using thus far assumes a constant force. It's force times displacement times cosine of the angle. This assumes a constant force and a displacement that's in a constant direction and a constant angle between their directions. So when one of these things is not constant, we have to account for that. That's what we just did with the baseball problem, where the direction of the force and the direction of the displacement were not constant, so we ended up with an alternative formula for work that used force and total distance rather than force and total displacement. Kind of the same idea going on here. We've got something that's changing over the course of this displacement, so we have to account for that. So when it's compressed, the spring force is a maximum. Actually, did we ever talk about spring force? I know I may have written the formula once or twice, but spring force is equal to negative kx. This is known as Hooke's law. Springs that obey Hooke's law are called ideal springs. And yeah, basically what it's telling you is that the spring force is, well, because of the negative sign, that tells you that it's opposite in direction to the displacement of the spring itself. So if you pull the spring to the right, it pulls back to the left. The force it pulls with would be to the left if it's been stretched to the right. If you compress it to the left, it pushes to the right. So that's what the negative sign is all about. Usually, the way I will use this is I will just use the magnitude and drop the negative sign from the equation and determine directions from my diagram instead. And in case I didn't comment on it before, this K factor over here accounts for the stiffness of the spring. Actually, I feel like I did cover this. I vaguely remember bringing this stuff out, but here's a spring that is going to have a pretty high K value, compared at least to my slinky. Let me go grab that. This thing has a very low K value. I can stretch it a lot and I don't feel a lot of pullback. I don't feel a lot of force from it. So the force per distance stretched or compressed, in this case I can only stretch it. It doesn't really do anything if I try to compress it. But the force per distance stretched is rather low. It's pretty loose, it's not very stiff, versus this thing, I have to pull on it a lot. I have to pull with a considerable amount of force, at least compared to this thing, in order to get it to stretch by any meaningful distance. So yeah, that's Hooke's law. If I stretch it double the distance, I would feel double the force in the spring pulling on me. Actually, yeah, I did talk about springs. Hold on, it's coming back to me. Yeah, and I brought out my spring scale, and we talked about, it was in one of the force streams where I was doing force problems. Yeah, it's coming back to me. I talked about that stuff. Of course, I know some people didn't watch some of those force problem streams because they felt that they already knew force. I hope you know what you're doing if that's you. Because I picked out the problems that I did in those streams for a reason. And I think you ought to watch them and learn from them. But I digress. I've said that way too many times today, haven't I? Anyway, at full compression, this spring force is at whatever magnitude, some sort of starting magnitude, and as it decompresses it, the X over here will decrease until it reaches this point where it reaches the original zero stretch, or in this case, zero compression distance. So the spring force is going to linearly decrease until it hits zero. So the force is not constant. But here's the good news. Here's the good news. We can still calculate the work done here. We can still calculate the work done by the spring force. Or, well, the work that could be done by the spring force. The work that the spring force would have to do, if allowed to push this block from here to here, can be calculated by using the formula 1/2 kx squared is what we get. Where does this come from? Well, it comes from calculus. Fortunately for you algebra-based students, we have a really simple graph that doesn't have a bunch of curves in it, so we can still derive this formula without calculus. As I argued in the kinematics chapter, if I'm remembering correctly, if you had the classic scenario that we've been doing, which is just some constant force, I guess we'll call it force applied, but it can be any type of force, versus position. If you had a constant force, the graph would look like this, right? Just a constant value of whatever. And we would say that the displacement is just going to be whatever this is. This would be our delta x, and then whatever our force is over here, F0, the area under here would just be F0 times delta x. Of course, this doesn't show you the cosine part of the work formula, but you've got the F delta x part of it at the very least. So this tells me that area under a force versus position graph gives me work. Okay, what's the area of this triangle then? If I can figure out the area of this triangle, then I can figure out the work. The cosine part of it, well, let's see. The spring force, when it's compressed to the left, the spring force would have to act to the right. So if the spring force acts to the right and displaces the block to the right, then right versus right, the angle between those is 0, so that would give me a cosine of 0, which is 1. So there you go, the cosine part of the work formula is accounted for. So now what's the area of this? Well, this was the spring force at maximum compression. How far was it compressed from its rest position? By this much, delta x dc, right? So this over here, this, I guess we'll call it F max up here. This F max is equal to K times the maximum delta x, the delta x dc, at least its magnitude. Okay, so now we have the height of our triangle. What about the base? The base is from here to here, from your starting position to your ending position. That's your delta x dc. And now we just use the area formula for a triangle. 1/2 base times height. Work due to the spring force is 1/2 base times height is equal to 1/2. The base is delta x dc, and the height of this triangle is K times delta x dc. So the delta x is just going to be squared, so we've got 1/2, and then the K, and then the delta x dc is squared. We usually don't write the delta or this dc thing. We just call it 1/2 kx squared. So that is the work that the spring would do if released. Before release, though, we can just say that that's work that we have pre-calculated as potential energy. In this state, it doesn't have 1/2 kx squared of kinetic energy yet, but if released to this point it will. So that's what we're going to call the spring or elastic potential energy. I'm going to call it PES for spring, but I know some teachers will also call it PEE. PE elastic. Actually, I think a lot of teachers use a lowercase e here, but I don't know. I don't like it. I'm much more comfortable with the S, because having to write 2 E's in a row and just saying it out loud, you could easily be misheard, especially if you're talking to, your study group members, if you're in a study group or something like that, if you're trying to communicate with other people. When you say PEE really fast, they might only hear 1 E and not understand you. So that's just one of the things that I don't like about it. So I'm just going to call it spring potential energy, even though that's not the official term. 1/2 kx squared, where this time you actually don't get to set your 0 willy-nilly. This time the actual x equals 0 position is determined by whatever the original unstretched length of the spring is. If I have a spring over here and I pin down one side like this, here is my x equals 0. I don't have a choice in this. This is my x equals 0 position, and then from there, if I want to stretch or compress it, if I compress it like this, then, can you even see that, or am I blocking it? If I compress it like that, I guess I'm not doing a very good job of compressing it. If I compress it like that, then whatever that distance is, I don't have a third hand, so I can't really show this very well, but whatever that distance is from the pen, we would use that as our x, and then if I were to stretch it like this, whatever that stretch distance is now going to be our x. Our x equals 0 position is where I left my pen right there. We don't have a choice in that matter. We can't just pick willy-nilly like we could with gravitational potential energy, where we could set the zero height to whatever we want. Don't have that luxury for springs. But yeah, there you go. That's the formula for elastic potential energy. 1/2 kx squared, assuming it's an ideal spring that obeys Hooke's law. If it's not an ideal spring, then for Physics 1, you don't have to worry about that. Physics C, once we get to the calculus-based review, we will take a look at an example or two of how to do the calculus for non-Hookean springs. But basically, whether it's springs or really any other variable force for you calculus-based students, it's the same idea. You're going to have some graph. It's not going to be simple geometry like this. It's going to be more curved and whatever. And you just calculate the area under the curve using your integrals. And if you don't know what integrals are, we'll go over that when we, again, get to the calculus part when reviewing. Seems like a long ways away, but what is it? We're 4 months away from the AP exam? More or less. I'm going to have to look at the schedule and see how much more we have left to do, because my estimate was that I would finish in around March, and I think I am slightly behind on that. If my original estimates were correct, I'm going to have to just by myself take a look at how much more there is left to go. But we are almost done with energy, so yeah, I think next episode, stream, whatever you want to call these parts, next part, we will probably be wrapping up the energy chapter, because the only thing we'll have left after this is power, which isn't really all that exciting, and we'll probably use most of the next part for doing more practice problems. Anyway, let's take a look at a problem now that we've learned about spring potential energy. Let's take a look at a problem involving springs. So here we have the launching mechanism of a toy gun. Consists of a spring of unknown spring constant. K is unknown. Okay. As shown in the figure, which I will draw for you. So we have, actually, I think if I remember correctly, I need to draw this 3 times. So they have a spring gun. I'm not going to draw the whole gun, but they've drawn like an X-ray vision inside the gun picture, and they're showing you that inside the gun you have, I should have drawn this lower, oh well, inside the gun you have a spring that is completely compressed, and there's like a plastic ball that's used as the toy bullet, and then later on they're going to ask us how fast will it be when the spring is completely relaxed, when it goes back to its original length. So I'm going to say that's going to be my scene 2. So this is the spring when it's relaxed. And then scene 3 they did draw. For some reason they skipped drawing scene 2, but scene 3 they did draw, where the spring is at its relaxed length, but is no longer in contact with the ball because it's been a few seconds and the plastic ball has been launched up into the air. Not drawn to scale, because if I drew this to scale, it would actually be much higher than that. So, pardon the unrealistic scale. The numbers are going to look very, very crazy given my drawing. But that's the space I have to work with, and again, I didn't plan far enough ahead. So they were saying, if the spring is compressed a distance of 0.12 meters, so our x equals 0 line, or if you want to call it a y equals 0 line for the spring, is over here. I'm going to call it x equals 0 because it's not really that big of a deal to me. So there's our x equals 0 line, and they said the spring is compressed a distance of 0.12 meters. So they're saying this gap is 0.12 meters wide. 0.12 meters wide. If the spring is compressed a distance of 0.12 meters and the gun fired vertically as shown, the gun can launch a 20-gram projectile, so mass of the object is 20 grams, which is equal to 0.02 in kilograms. It can launch a 20-gram projectile from rest, so V of scene 1, I will call it V1, is equal to 0. The gun can launch the projectile from rest to a maximum height of 20 meters above the starting point of the projectile. Above the starting point. The starting point is all the way down here. So it's 20 meters from down here. And it goes up to a maximum height of 20 meters. And yeah, you can already see why my drawing is not to scale. This is 20, while this is 0.12. This looks like a third or maybe a fourth of this. So yeah, my proportions are out of whack, but we'll work with it. If you want to draw a more realistic drawing on your paper, because this is messing with your head too much, feel free to do so. I would probably do the same if I were doing this with pencil. Neglecting all resistive forces, so no friction, no air resistance. Determine the spring constant. So first thing they're asking us is what is K? And then part B, determine the speed of the projectile as it moves through the equilibrium position. So over here, what is the velocity in scene 2? What is V2? So I guess I should label these scene 1, scene 2, and scene 3. And, oh, and that's it. I thought there was going to be a part C over there. Okay. So let's get started with this. Let's go ahead and figure out what forces are acting on our object. So they said neglect resistive forces, no friction, no air resistance. We're good there. The force acting upwards on this thing is going to be the spring force. And the force acting downward on it is going to be gravity, and that's it. Well, spring force and gravitational force are both conservative forces. I didn't prove it in the case of the spring, but you can play around with it. In fact, maybe I should make that homework. Well, the independence of path is... The path is kind of set already for a spring, so I guess this isn't really... You're not going to have a curved path for something that's being moved by a spring, whether it's pulled or pushed. So I guess you don't need that. Maybe as an exercise, I will let you try and demonstrate that work done by a spring can be reversed by reversing the path of the object that's hooked to the spring. That might be something fun to do on your own. But anyway, finding K and V2. So since our only forces are conservative forces, we know what the non-conservative work is. Non-conservative work is equal to 0. You can't have non-conservative work if you don't have any non-conservative forces. That's the easiest scenario that you can have. Well, maybe I shouldn't say easiest, because when springs are involved, it makes it so that you can't do that one trick that we did earlier where we got to cancel out all the mass. Unfortunately here, even though the non-conservative work is 0, because the spring potential energy doesn't have mass in it, we can't cancel the mass out everywhere, which is why they actually gave us the mass for the problem. Anyway, so I can do my energy equations, my mechanical energy between scene 1 and 2, or between scene 2 and 3, or between scene 1 and 3, because at no point from scene to scene, at no point are any non-conservative forces doing work. If I had a situation where from scene 1 to scene 2 there was some non-conservative work, and then from scene 2 to scene 3 there was no non-conservative work, then I would actually have to do, I couldn't just skip from 1 to 3 in that situation. In that situation, I would actually have to go chronologically, but since since the non-conservative work is 0 between all scenes, I can compare any pair of scenes among these 3 that I want. So let's see if we can choose what's most convenient for us then. In scene 2, I do not know what V2 is, so that's introducing another unknown that I'm probably not ready to deal with. So I think our best choice here for part A, for finding K, would have to be scenes 1 and 3. Let's see what we can do with that. Between scenes 1 and 3, and let me switch colors. What color do I want to use? I guess I haven't really used you in a while. So, scene 1, we've got, what's the mechanical energy? We've got 1/2 m v1 squared. v1 is 0, so that's out already. Plus potential energy gravitational. I will go ahead and set this to my 0 height. You could have also used this over here as your 0 height. Those are both good choices, but I'm just going to pick the very lowest point and use that as my h equals 0 position. So that's going to be mg h1, h1 being 0, of course, so that's a 0. So far looking good. And then the other part of our potential energy, now we have a spring, and it is not at its regular length. It is not at its unstretched, uncompressed position. It is not at its equilibrium position, is what it's officially called. Which means there is some spring potential energy, 1/2 k x squared in here. The x being 0.12. Okay. Plus 0 non-conservative work between scenes 1 and 3. So plus 0 non-conservative work equals, in scene 3, if it's at its maximum height and it was fired straight up, then we don't have horizontal components to worry about, so it's not going to be a situation like this guy over here who still had some speed at his maximum height because he launched at an angle and had some horizontal motion. This thing was fired straight up, and it didn't have any initial horizontal motion, so it shouldn't have any final horizontal motion. So at its maximum height, At the maximum height, the vertical velocity should be 0. And since the horizontal velocity is also 0, the total velocity is 0. So v3 is 0. So 1/2 mv3 squared kinetic energy at the maximum height is 0. Plus potential energy at the maximum height. That's going to be mgh3, whatever h3 is. I guess h3 is measured from the bottom, so that's the 20 meters. h3 equals 20 meters. And then for the spring potential energy, that's going to be 0 because, well, the spring is uncompressed. In scenes 2 and 3, in both of these scenes, there's no spring potential energy to write into our equation. Okay, so that just leaves two things. 1/2 k, and then the x was from here to here is 0.12. It doesn't matter if it's positive or negative because the formula has you squaring the x anyway, so it doesn't matter which direction the spring is pulled or pushed. You don't have to worry about positive versus negative here. Equals mgh3, so m was 0.02, g of course is 9.8, and h3 was 20. Okay, so take your 0.12 squared, which I guess is going to be 0.0144, and divide by it and multiply everything by 2, and that should get us k. So k is, and I see a question in the chat, I will get to you in a minute. K is going to be 0.02 times 9.8 times 20, and then divide by 0.12 squared, and multiply by 2, and that's giving me 544.44 with a bunch of repeating 4s. And the units of the spring constant would be newtons of force per meter of stretch or compression. Now for your question, how is kinetic energy related to momentum? We have not gotten to the topic of momentum yet, but if you must know, I guess this is a little preview for the rest of you, momentum is mass times velocity, or if you just want the magnitude of momentum is just the mass times the magnitude of the velocity, mass times the speed. Since kinetic energy is 1/2 mv squared, what you can do is you can take this magnitude of momentum and square it, so you can do magnitude of momentum squared is equal to m squared v squared. Now, if I divide this by 2m, then I get p squared over 2m equals, I can cancel one of the m's, and then the 2 over there I can just pull out as a 1/2 mv squared, and there you go. Kinetic energy is equal to momentum squared over 2m. That's a shortcut formula that is sometimes used. But yeah, the other relationship between momentum and kinetic energy is for, at least the one that comes to mind for me, is for perfectly elastic collisions, which is a rather big topic that I will be saving for when we get to the momentum chapter. So if you can't afford to wait for that, I would recommend trying to look up some other videos from other physics channels discussing that topic. Hopefully that question, or that answer to your question, is satisfactory. Now then, back to my problem at hand. We just got the spring constant over here, which was part A, so we can check that off. And next part, we want to find what is V2. Let's see, is there a way to do this without having to rely on this k value that we just calculated? Probably not. Let me see, if I compare scene 2 to scene 3, would that work? If I do mechanical energy between scenes 2 and 3, so I don't know V2, I do know V3. I know spring potential energy for both is going to be 0, so that's eliminated. Oh, yeah, I can do this. Yeah, this will work. We just have to do a little bit of math, a little bit of working with decimals. So we can do, between scenes 2 and 3, I can do 1/2 mv2 squared plus mgh2. H2 is going to be the real trouble here, but not too terrible. Plus there's no non-conservative work being done between scenes 2 and 3, equals 1/2 mv3 squared plus mgh3. And there's no 1/2 kx squared for either of them because, again, spring is at its equilibrium position in both of those scenes. This, we said earlier, was 0, right, at the maximum height, no vertical speed. And then H3 is 20. H2 we don't have yet. H2 is up here. So we've got 20 is all the way up here, and 0 is down here, and this is, oh, actually we have H2. Never mind. I thought we had to subtract 20 and 0.12 for some reason, but I guess that was just my brain thinking a little too far ahead. So yeah, we can just do 1/2 times 0.02 times V2 squared plus 0.02, I'm just going to keep it as G for now, times H2 is just from here to here is just 0.12. So that's mgh2 plus nothing equals, that's a 0, and then mgh3 is 0.02 times G times H3 is 20. Oh, and I guess we can just cancel the 0.02 everywhere. Yeah, I forgot, since the spring potential energy isn't here to throw a wrench in things, all the terms have mass in them, so we can cancel it all out. Okay, that's good. So I guess we could have actually solved part B before part A if we wanted to. Okay, so subtract 0.12 G from 20. Yeah, there we go. That's why I was thinking we would have to subtract. Yeah, I was thinking a little too far ahead. So 1/2 V2 squared equals, if I subtract 0.12 G from 20 G, that's going to be 20 minus 0.12 all times G, and then multiply by 2 to cancel that 1/2. So 20 minus 0.12 is 19.88, and then so we have 2 times 19.88 times G, which is 9.8, is 389.648. That would be V2 squared. Don't forget to take the square root. That's probably the most common mistake in this chapter, is forgetting to square root your V squared. And I'm getting 19.7395. I'm going to round that to 19.74. So I get V2 equals 19.74 meters per second. And there we go, there's that problem done. All right, it looks like we've got half an hour, so maybe we can squeeze in 1 or 2 more problems. Let's see what I want to include. I think I spotted a certain problem earlier. Oh, hold on. I think... no, that one is not quite the problem I'm looking for. Let me see, maybe it's on the next page. And nope. Actually, that might be it. Yeah, upon second reading, I think this is it. So, yeah, let's take a look at this next one. So it says, Tarzan swings on a 30-meter long vine. So we've got, here's a picture. Here's Tarzan. I'll draw the vine in a minute. I want to draw it in a different color. Since it's a vine, we might as well draw it in green. And I don't think I drew this low enough, but there you go. There's a vine, and its length is equal to 30 meters. It is 30 meters in length. And then there's, I guess, a body of water over here. And what else does it say? So he swings on a 30-meter long vine, initially inclined at an angle of 37 degrees with the vertical. So my angle might be off, but this is supposed to be 37 degrees initially. What is his speed at the bottom of the swing if he starts from rest versus if he pushes off with a speed of 4 meters per second? The hard part of this problem isn't even the physics, it's the geometry. So he's going to swing, and of course down here at some point he will reach his lowest point somewhere down here. I guess I drew that water exactly at the right height. And the question is, what is his velocity down here? We know it's going to be tangent to the path, or parallel to the path, rather. Yeah, tangent, parallel, same thing in this case. So this is going to be his V bottom. And yeah, what is that going to be if V initial is 0 versus part B is asking if he pushes off with 4 meters per second. So part A, if V initial equals 0, and then part B, if V initial equals 4 meters per second. The question is, what is V bottom in each of those cases? There are two important takeaways from this. One is the geometry takeaway. The other one is going to be, will V bottom in part B, will it be 4 meters per second more than it is in part A? Yes or no? Make your predictions now. And let's see whether or not we have any misconceptions to address. So a lot of students will get stuck on this because they might recognize that they have to use mechanical energy in some way, but they can't find the height for potential energy. So here's what you need to do. Since this is a vine, if you swing along a vine, if you were to allow yourself to just, if you pushed off with a high enough speed, you could swing around in like a complete circle. So what I've drawn here is actually a slice of a circle, if you think about it. And if you think about it that way, then the distance from this point where the vine is attached to any other point on this path is the same, which means this over here has to be 30 meters. Some of you might be having flashbacks to what I showed you in the Math Essentials way back when we first started this whole streaming series. I started with the Math Essentials for a reason. Today you're gonna learn. Today you're gonna learn why. So his initial height is gonna be somewhere over here, and his final height is gonna be somewhere down there. And I need to calculate how far apart these two heights are. This is, I guess we'll call it delta H. How far apart are those things? So this is 30. I need to subtract this much from it in order to get my delta H. And the good news is I have a right triangle over here. If you see it, it goes like this, and then up. And hypotenuse is 30 meters. So this over here is 30 cosine of 37 degrees. Right? The part of this green triangle that's touching the 37 degree angle, that must be the cosine component. So 30 cosine 37 would be the length of that. And let me think, cosine of 37 is what, 0.8-ish? So 30 times 0.8 is 3 times 8 is approximately 24 meters, which means delta H would have to be approximately 6 meters. I know if you put cosine of 37 into your calculator, it's not exactly that, but 37 and 53 are rather special angles. They usually, when they write these problems, they usually expect you to recognize that it's your 3, 4, 5 or 6, 8, 10 triangle. So I'm just going based off of that, what I think the author's intent was when writing the problem. So now that we know our delta H is 6 meters, we can just set our zero height. I'm just going to use the bottom as my H equals 0 line, which means up here where Tarzan starts is going to be at H equals 6 meters. And now the rest is just going to be usual mechanical energy stuff. What forces are acting on Tarzan while he swings from this point to this point? So he's going to lift his feet immediately off the ground, so we will ignore the normal force because it only exists for a split second. I'm only concerned about the forces that act on him from the moment he lifts his feet off and during his time swinging down over here. And let's assume he doesn't touch the water, so don't assume that the water down here has any effect on him. What forces would be acting on him? He's holding onto a vine, so there's going to be a force of tension. And other than that, the only thing acting on him would have to be a force of gravity. I don't see any springs. They didn't mention anything about air resistance, so we can neglect that. That's our usual assumption, that air resistance is negligible. If it's not mentioned, we can neglect it. No friction, no air resistance, no normal force, because again, we're starting from the moment after he lifts his feet off the ground. And I think that's it. And no applied forces either that are acting on him. I mean, he's applying a force to the vine, but the vine applying a force back to him, we already accounted for that. We called it tension. So yeah, tension and gravity are the only forces acting on him. Tension is non-conservative, so how much work does it do? What is our non-conservative work? Always start by asking yourself, what is the non-conservative work in these sorts of problems? Non-conservative work here is just the work due to tension. The direction of tension is always going to be radially inward towards the center of this circle that he's moving along, towards the center of this circle that his path partially traces out. He doesn't go in a full circle, but he goes through a circular segment. His force of tension is always, the force of tension on him is always towards the rope, so towards the center of this circular path. His displacement at any moment in time, if we, again, the same thing we've done, twice today, chop up his motion into little segments. If we chop up his motion into little segments, like this, into little straight segments, at each segment, the force of tension acting on him is going to be perpendicular to that segment, while his displacement is going to be parallel to that segment. So the angle between the tension force and the displacement at any given moment that you freeze him in time will always be 90 degrees. He will always have his tension force acting 90 degrees to his displacement. So that's just going to be force of tension, whatever it is, times displacement, whatever it is at any given moment here. I'll draw a couple more just for the sake of illustrating. Wherever he moves, the direction of the tension force moves with him, and so does his displacement, and they're always in such a way that they're at 90 degrees to each other. So that's a big old zero. Zero work due to tension, zero non-conservative work overall. Okay, so mechanical energy equation, mechanical energy initial plus non-conservative work equals mechanical energy final. We have 1/2 mv initial squared. I know it's 0 for part A, but I'm going to keep it like this without crossing it out because we're going to need it again for part B, plus mgh initial equals 1/2 mv final squared plus mgh final. Good news, everything here has an m in it, so I can divide the whole equation by m, and that cancels out. Okay, and I can also multiply by 2 to get rid of that fraction, and I get v initial squared plus 2gh initial equals v final squared plus 2gh final. Be careful and make sure that you actually multiply the 2 into every term in your equation if you're trying to cancel those fractions. A lot of students will forget to do one side or the other, or they'll forget a term here or there, so be careful with that. Okay, h initial is going to be at 6 meters. H final we've set to 0 meters, so that's a 0, that's gone. So that just leaves us with v final squared equals, in our first case for part A, 0 squared plus 2g is 19.6, and then h initial is 6 meters. Oh wait, v final squared rather. Almost made a mistake there. And then square root of 19.6 times 6 is 19.6 times 6 is 1117.6, and the square root of that is 10.844. So I'm just going to say 10.84. So for part A, v final is 10.84 meters per second. All right. If you haven't made your predictions, make your prediction now. Is v final in part B going to be 14.84 because he initially starts with 4 meters per second? Yes or no? Lock in your answers now. So take that formula again. This time we're going to do v final squared equals v initial squared is 4 squared plus 2gh initial, so that's 2g 19.6 again, h initial 6. let's see. Square root of 4 squared plus 19.6 times 6. I'm getting 11.5585. I'll round that to 11.56. So for part B, I get V final equals 11.56 meters per second. Or I guess I called it V bottom, but you know what I meant. So there you go, 11.56. Kicking off with 4 meters per second did not actually give you 4 more meters per second of extra speed at the bottom. And that should make sense if you understand how square roots work. What we essentially did was, let's see, how do I phrase this mathematically? My brain is a bit too fried now. I need to pause and think about this. So, if I did something like, is x squared plus y squared equal to, is the square root of x squared plus y squared equal to x plus y? Because that's essentially what the reasoning would have been if you thought it was as simple as adding 4 over here. Is 4 squared plus this stuff equal to the square root of 4 squared plus the square root of this stuff? The square root of this stuff being 10.84, the square root of 4 squared being 4. Clearly not, right? I should have put a question mark over there. Sorry about that. Is this relationship true? I guess only when x and y are equal to 0. That's the only way it would work. How would I go about doing this? I think I actually want to sit down and do the math here. I'll square both sides, so that gives me x squared plus y squared is equal to, if I square x plus y, then I get x squared plus 2xy plus y squared. And if I subtract x squared on both sides and subtract y squared on both sides, I get 0 equals 2xy, which implies that either x equals 0 or y equals 0. So yeah, those are the only 2 scenarios where that would be true. Okay, that was a nice little mathematical detour, I guess. Let's have a look at one more problem before we wrap things up for today. Oh, here's a fun one. Ready to think about systems? I think I brought this up last week. 3 objects with masses m1 equals 5 kilograms, m2 equals 10 kilograms, and m3 equals 15 kilograms. 5, 10, and 15. Let's draw this table that they have. So they have a table, and they have some pulleys. Don't you miss pulleys? That's M2. That's M1. And that is M3. They drew them different sizes in the book, but I'm not going to worry too much about that detail. I guess I haven't used orange in a while. So it says the 3 objects are attached by strings over frictionless pulleys. So let me list up here M1. Actually, I remember when reviewing the video last time, over here it's too close to the light, it doesn't show up too well. Let's do it over here. M1 equals 5 kilograms, M2 equals 10 kilograms, and M3 equals 15 kilograms. Okay, there's our data. So, what did we have? So it said they are attached by strings over frictionless pulleys as indicated in the figure. The horizontal surface is frictionless, so no friction. Frictionless surface. I don't know why I've been going out of my way to write the word frictionless today, but I will probably go back to old habits next time, so don't expect me to write when the situation is frictionless. I'll just say it verbally once or twice and that'll be it. The horizontal surface is frictionless and the system is released from rest. Using energy concepts, find the speed of M3 after it moves down a distance of 4 meters. So after this thing moves down, I guess I'll call it delta y this time. Delta y is 4 meters. I guess I would call it delta y3. Well, actually it doesn't matter because all of them will have a displacement of 4 meters. If this thing moves down 4, then this moves right 4, and this moves up 4. So a lot of students will correctly, through their intuition, be able to solve this problem just fine. But I think it's valuable to slow down and really analyze what this problem is telling us about systems of objects. They are all released from rest. That's another thing I should note. V system initial, I'm just going to say V system initial is equal to 0. So that's another thing to take into account. I'll use my light blue over here. So, is mechanical energy conserved? Let's take a look at one block at a time and see what's going on. So, on block 3, you've got, I guess we'll call it force of gravity 3 downward, and force of, I guess we'll call it tension 2 upward. Force of tension 2 upward. And that should be it. On M2, you've got force of gravity 2, which is canceled out by this normal force. And then there's also force of tension 2 pulling it to the right, and force of tension 1 pulling it to the left. And then M1 has force of gravity 1 pulling it down, and force of tension 1 pulling it up. Well, tension and normal force are non-conservative forces, so we need to figure out how much work they do. Object 2, the normal force isn't going to do any work on it, neither is the gravitational force going to do any work on it, because its motion is going to be horizontal while those two forces are vertical. 90-degree angle, you know the drill by now. No work done by those two forces, but the tension forces will do work because they are completely parallel to M2's motion. So that's something we're going to need to account for. And if the system is going to accelerate at all, after all, it started from rest, then one of these forces is bigger than the other. So, uh-oh, do we have a problem here? Do we have a problem? Well, let's see. So, work non-conservative on block 1. If block 1 moves up 4 meters, then the non-conservative work would be force of tension 1 times the 4 meters times cosine of 0 times cosine of 0 degrees, because the displacement is up and force of tension 1 is up. So that's going to be positive 4 force of tension 1. Okay, what about the non-conservative work on block 2? We're going to have, from force of tension 1, it will be displaced, its displacement is 4 meters, and then tension 1 is at 180 degrees to the displacement of block 2. Displacement of block 2 is to the right, tension 1 is to the left, so that's going to be cosine of 180, which is going to give us a -1. Plus, it also has the work done on it by tension 2, plus force of tension 2 times the same displacement, 4, times cosine of, this time it's going to be cosine of 0, because tension 2 is in the same direction as the displacement of block 2. So that's going to be -4 force of tension 1 equals -4 force of tension 1 plus +4 force of tension 2. So that's the non-conservative work on block 2. What about the non-conservative work on block 3? It moves down 4 meters, tension 2 is up, so those are going to be at 180 degrees to each other. So that's force of tension 2 times 4 times cosine of 180. That's going to be -4 force of tension 2. And you might notice something. What's the total non-conservative work across all 3 objects? You might have noticed already. It adds up to 0. Work non-conservative 1 plus 2 plus 3 plus non-conservative work on object 2 plus non-conservative work on object 3 is 4 tension 1 minus 4 tension 1 plus 4 tension 2 minus 4 tension 2. It's just equal to 0. So work non-conservative on the system is equal to 0. Oh, well, would you look at that? And then if I did my mechanical energy equation for each object individually, I would end up with 3 equations, which, if I added them up, would result in a scenario where my mechanical energy is conserved. So mechanical energy isn't conserved for any of these blocks individually. Not a single one of these blocks has a 0 non-conservative work on it. Individually, none of them have their energy conserved. Some lose, others gain. None of them remain at the same energy that they started off with when the system was first released. But the system as a whole, whatever energy was lost by one block was gained by another one, and vice versa. So I can just write my mechanical energy equation in terms of the whole system. I can do 1/2 m system v system squared plus, well, actually, hold on. No, I don't want to do it this way. Let's do it this way. Let's do it by adding the kinetic and potential energies of all the blocks together. So I'm going to do kinetic energy 1 initial plus kinetic energy of block 2 initial plus kinetic energy of block 3 initial plus potential energy of block 1 initial plus potential energy of block 2 initial plus potential energy of block 3 initial plus your total non-conservative work plus all three of these, which we already determined to be 0, is equal to kinetic energy 1 final plus kinetic energy 2 final. Yeah, I know it's a hassle to write all this, but the point is you only have to do it once to kind of process what this problem is trying to teach you. And from that point on, you can just take the shortcut because there are going to be a whole bunch of zeros in this. And then potential energy 1 final plus potential energy 2 final plus potential energy 3 final. Okay. Kinetic energy initial, all of them were initially at rest. So 0, 0, 0. Potential energy 2 initial is equal to potential energy 2 final because block 2 does not change in height. It doesn't go up or down. So whatever you set your 0 height to, it doesn't matter as far as block 2 is concerned. Whatever its MGH is, it has an equal MGH on the other side of the equation, so those cancel out. So now all that's left is potential energy gained by block 1 rising and potential energy lost by block 3 falling 4 meters. And kinetic energy gained by all 3 blocks. And yeah, that's it. So potential energy 1 initial minus 1 final. I guess I could move that over. Yeah, I could move this over to the other side of the equation. Do I have enough room for this? I really don't want to start a second sheet for this. I guess I could do it up here. Let's see. So M1 G and then H1 initial minus M1G H1 final. So I can factor out the M1G and just do this. H1 initial minus H1 final. So that's subtracting potential energy 1 final from both sides. And then do something similar for block 3. So plus M3 G H3 initial minus H3 final. Okay, so that's one side of the equation equals, now that I've subtracted this and this, that just leaves all kinetic energy on the other side of the equation. So that's going to be 1/2 m1 v squared plus 1/2 m2 v squared plus 1/2 m3 v squared. I can factor out the v squared, and that leaves me with m1 plus m2 plus m3 inside the parentheses, and then v squared, v final squared of the system. Must be the same for all 3 of them. Okay. And I can just plug in my numbers now. I don't even need to establish what my h's are. I just need to know the changes in h. So h1 initial minus h1 final. h1 initial is somewhere down here. h1 final is 4 meters higher. So the lower minus the higher, that's going to be -4. This is going to be a -4 over here. And then h3 initial minus h3 final. This thing started 4 meters higher than where it ended, so starting height minus ending height is positive 4. The starting height is 4 more, so that's positive 4 meters for H3 initial minus H3 final. Okay, so negative 4 m1g plus 4 m3g equals, and then I guess multiply that by 2 and divide that whole thing by m1 plus m2 plus m3. I think I can squeeze that in over here. So it's going to be negative 4 m1g plus 4 m3g all over, I'll keep the 1/2 in there with them, m1 plus m2 plus m3. That's going to be equal to v final squared. And then we can just take the square root of that. So let's see. m1 plus m2 plus m3. 5 plus 10 plus 15 is 30. And then half of 30 is 15. So we've got 15 in the denominator. Let's go ahead and type that in. And then negative 4m1. So negative 4 times 5, that's negative 20. And then positive 4 times 15. So that's positive 60. So that's plus 60. And then all that times g. So times 9.8. Did I do that right? Negative 20, positive 60. Yeah. Times 9.8. I'm getting 26.133. That's v final squared. And if I take the square root, whoops, forgot to copy that in. Let's see, square root of, wait, what am I doing? Square root, there we go. Square root of that is about 5.112. I'll just round it to 5.11. So V final of the system, I am getting 5.11 meters per second. So there you go. Systems thinking still works in some energy scenarios. So hopefully you will remember the importance of starting all your mechanical energy problems with the important question of what is the non-conservative work? Is it 0 or not? Don't just assume that mechanical energy is conserved. Don't just assume that your non-conservative work is 0. It very well may not be. And also, don't assume just because there are non-conservative forces present, as in these past couple of problems, that necessarily means that they do some work. That may not be the case. You can still have non-conservative forces present and have energy still be conserved. So you have to actually think about the directions of those non-conservative forces and the direction of the displacement, which is sometimes easier said than done because sometimes your objects move in a curved path and you have to kind of think of it like this, chop it into little straight segments and think of what implications that has to the work being done by whatever forces are acting on the object as it turns and curves. But yeah, hopefully this has given you enough to do a lot of energy problems. That's what I would recommend for between now and next part. Just go through your textbook. If you have your own textbook, go through the textbook listed in the course plan and start doing those mechanical energy problems and start practicing them. And just do a whole bunch of them. And like I always say, once you finish a problem, reflect on it. Ask yourself, what did I learn from this problem? See if there's anything extra you can do that might teach you something. If you see something that looks curious, if, for example, in this Tarzan problem, when we ask the question, if you start with an initial speed, how much does that actually add to your final speed compared to when you had no initial speed? Ask yourself those kinds of bonus questions. Try to figure out what your misconceptions are and see if you can just dispel them with your own math, with your own work. And if you're not sure, go online and post questions. Ask in forums. You can ask in the comments here or in the chat or whatever. And yeah, just continue those best practices. Next time, we're going to give a quick introduction to power and do some power problems and probably run out of power problems and just do some more work and kinetic and potential energy problems from there. So, yeah. Any other announcements? Let me think. No, I don't think I have any. So, yeah, I guess that'll be it. Hope you learned something valuable today. Class dismissed.